Okay, guys, good afternoon. So, okay, good afternoon. Yep. I'm not really where I want to be with respect to marking your papers. So apologies for that. I hope soon everything will be more regularized. We still have a little bit of review, and then we have to introduce some examples of groups. So what I want to review a little bit today. So let's see. So today's February 1st, and oh, someone came in. And today I want to talk about homomorphisms, a little bit, remind you what those are, and I want to also talk about generators and relations. Because that will give us kind of like a recipe to make groups up. Okay, so that'll be a good source of examples. Okay. Okay. So first of all, let me remind you what a homomorphism is. Then we'll do a quick example. Definition. Let G and G prime be groups. So if we have a function phi from G to G prime is called, and our function is going to be called phi in this case. Oh, someone else came in. Okay, and it's called a homomorphism. Well, if you remember linear algebra, the maps between vector spaces with respect, like scalar multiplication and addition, they get a special name. You know, even in calculus, the functions which kind of respect convergence of sequences, they get a special name, continuous. You know, here we're studying groups, so the functions with respect to group law, they'll be called homomorphisms, they'll be special. Okay. So it's called a homomorphism if phi of gh equals phi of g times phi of h for all g and h in G. Okay, and that's a homomorphism. Okay. A quick example. Define phi from the integers to z mod nz, where n is bigger than 1, by the rule phi of n, oh, not phi of n, phi of m equals the congruence class of m mod n. Let me remind you that that means this is a congruence class, so it is all the things of the form m. It can also be m plus or minus n, m plus or minus 2n, and so on. Okay, and define this for all m in z. Okay, this function is simple enough that we can kind of draw a picture of it, which I will try and do now. So let's say that n equals 6, then we can draw a picture like this. If n equals 6, that means there's 6 equivalence classes. There's the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, the equivalence class of 3, the equivalence class of 4, the equivalence class of 5. And, you know, to define our function phi, well, you take an integer and map it onto the equivalence class in which it lies. For example, so here's the domain, here's the codomain, and here I want to get an idea of the domain. So 0, it's mapped onto 0, -6, 6, 12. All of these things go to the equivalence class of 0. Right? Because the equivalence class of 12 is the same as the equivalence class of 0. Okay. And then we also have the equivalence class of 13, 7, 1, -5. All of these guys, they get mapped onto 1, the equivalence class of 1. Then you can kind of see what's happening. All of those get mapped to 2, and the same thing. It'll just continue on the picture. Okay. Okay. And now notice if I keep on going, the next thing I write would be 18, 12, 6, 0, -6, and so on. Well, I just go around to the back, or to the equivalence class of 0. So they kind of like, there's kind of like, it's kind of like a wheel or something, or a spiral. Or at least it's nice to think of it that way. Okay. So as you count up by 1, you go through all the equivalence classes, and then when you get to the last equivalence class, you go back to the first. Okay, and now to check that this phi is a homomorphism, for it to be a homomorphism, you need to check that phi of m plus m prime equals phi of m plus phi of m prime. That is, phi kind of needs to respect the addition of m and m prime. Okay. And then the definition of phi says that you just need to check that the equivalence class of m plus m prime is just equal to the equivalence class of m plus the equivalence class of m prime. Okay, so you need to check that for all integers m and m prime. Okay. But this is the definition of how you add equivalence classes. Okay. So it's something, you know, it's already, we know it holds already. So this is definition of addition in Z mod NZ. So it holds. Okay. Okay, so now we have a homomorphism. Okay. Just a quick property of just something to remember about homomorphisms. Let's say phi from G to G prime is a homomorphism. Then phi of the identity of G is equal to the identity of G prime. Okay, so going back to our example, the identity of the integers is 0, the integer 0, and the identity of the integers mod 6 is the congruence class of 0. And notice 0 maps to, like, the identity of Z maps to the identity of Z mod 6. Okay, and we're saying that always happens for homomorphisms. So we can write a quick proof. I'll start with the equation EG times EG equals the identity. So the identity times the identity equals the identity. Okay. That follows from the equation that the identity of G times little g equals G. Okay, since this is true, it's true when G equals the identity. Okay, so take this equation and plug in the identity for G, you get this. Okay, now apply the homomorphism phi to both sides. And you get phi of the identity times the identity equals phi of the identity. And now phi is a homomorphism. So phi respects the group law. So we can like kind of distribute the phi if you want to say it like that. Okay. That's since phi is a homomorphism. Okay. Okay. Now we have phi of phi of EG times something equals something. Okay. So however you want to do it, we can cancel this 5EG on the right. Okay, so let's cancel it. We see that 5EG equals the identity of G prime by cancellation. Actually, maybe that's not satisfying to you. I'll just write in an in-between step. Write 5EG as EG prime times 5EG, and now cancel those on the right to get this statement. Okay, so whenever we have a homomorphism, it takes the identity to the identity. It takes the identity of the first group to the identity of the other group. Okay. Okay, before I talk more about homomorphisms, so that's the end of the proof for this. But there's something else I want to talk about too, and that is generators and relations. And then after that, if we have time, we'll talk a little bit more about homomorphisms. Okay. Okay, so right now, here are the ways that I can give you examples of groups. Our examples of groups can come from, let's say, like, kind of, first thing, I'll call them like known structures, by which I mean, like, take something you've learned about in another class, and maybe it has something to do with group theory. Like, for example, the integers, the real numbers under addition, kind of like permutations, which you might remember or not. That's okay if you don't. N by N matrices. Many more. Okay. And then kind of the only other way so far is that I can just give you a set and write out the multiplication table. I'll say with a valid multiplication table. Okay, this is actually was fine for a group with 4 elements. Remember, I had this group V with the identity in ABC, and we wrote out all the like ways to multiply A, B, and C. Right, that's fine with 4 elements. With like 60 elements, now I have to write out 3,600 different ways to multiply, and then I might have to check the associative law. Is going to take a long time. It's like fine, but not good. So we need something, because we need to have, we want to know, because there's going to be a lot of groups that don't come from any of these. And we need a way to write them down. Okay, and for us, that means we need to talk about generators and relations. Oh, okay. Okay, so remember a set A in G generates G if every element of G can be written as like x1 to the e1 times x2 to the, or I'll say a1, x2 to the a2, all the way up to xn to the an for some n greater than or equal to 0. The a's, the exponents are either plus or minus 1, and the x's come from a. Okay. Okay, so that's when a subset generates a group. Okay. A relation is just an equation of the, I'll say it's an equation of the form x1 to the a1 all the way up to xn to the an equals the identity of G. Okay, that's a relation. Okay. And okay, and then let R be a set of relations satisfied by the elements of A if every relation of G can be deduced from the elements of R and also the group and the group axioms then we can write that, we write G is just kind of generated by A subject to the relations coming from R. Okay, and that is a lot more convenient because now I can just tell you like the generators and kind of some equations between them, and then you can go from there. As an example, okay, as an example, Okay. You define Cn, it's going to be the group that's generated by an element X, and the relation is just going to be X to the N is the identity. Okay. Now, if I want to know, in this group, everything is just powers of X. To multiply two elements of the group, well, it's just like you just use the normal exponents, addition of exponents. So in Cn, x to the 5 times x cubed, well, that's just x to the 5 plus 3. You also have like x to the minus 2 times x to the 4th. Well, that's just x to the minus 2 plus 4, for example. Okay, so let us take now just a 5-minute break. And then when we come back, we'll talk a little bit more about generators and relations and homomorphisms. Okay. So I'm going to end the meeting now and just rejoin with the same link. Okay. Thank you.